Hello students, in our today's class I am going to discuss about structure of diborane. Already we have discussed preparation methods and properties of diborane. So let us see the structure. It is an electron deficient compound. So what do we mean by the electron deficient compound? So before going to this meaning, we should know number of electrons calculation, number of bonding electrons calculation in the covalently bonded molecules. So number of bonding electrons can be calculated by 2 into Na minus 1 formula. Here Na is the number of bonding electrons, Na is the number of atoms. Okay, I am taking CH4 as an example now. CH4 is methane. Number of electrons can be calculated by 2 into Na minus 1. So number of atoms or number of elements here 5. 4 hydrogens, 1 carbon. So 2 into 5 minus 1. So 2 4s are 8. 8 electrons will be there in the CH4. So we can observe the structure of CH4. Carbon is having 4 valence electrons. It is forming 4 bonds with 4 hydrogens. 1 electron, that means each hydrogen is having 1 valence electron. So it is forming 4 bonds with 4 hydrogen atoms, CH4, and forming a tetrahedral structure. Okay, so let us see the second example. I am taking C2H6 because it is similar to B2H6 structure. So if I calculate C2H6 number of electrons, 2 into Na minus 1 again. So 2 into 8 minus 1. Here 2 carbons, 6 hydrogens. Totally 8. 2 into 8 minus 1. We are getting 2 sevens, 14 electrons. So 14 electrons are present in C2H6 structure. So if you calculate B2H6, we should also get 14 electrons. But electron diffraction studies proves that diborane is having only 12 electrons. So how it is getting 12 electrons? Let us see the hybridization of these two molecules. Then we can understand clearly. So C2H6 I am taking first. Carbon is having 6 atomic number, 6 electrons in its orbital. So 1s2, 2s2, 2p2. So I am taking only valence electrons. Only valence electrons involves in the bonding. So ground state 1s2, 2s2, 2p2. Okay, 2s2, 2p2. So 1 electron will jump to the next level in the excited state. So we are getting how many Sp3 hybrid orbitals? 4 Sp3 hybrid orbitals. So each carbon is having 4 Sp3 hybrid orbitals. So 3 unpaired electrons forms bonds with the 3 hydrogens. Okay. Next, here also, next carbon also forms bonds with 3 hydrogens, and last electron of this 2pz, another Sp3 hybrid orbitals, involves in bond formation with other carbon. So we are getting carbon-carbon bond, single bond. Okay. So totally if we calculate, here we are having 2 electrons, each bond is considered as 2 electrons, 2, 2, 2, totally 6 this side 12, and center 2. We are getting 14 electrons in the structure. So if we observe B2H6, boron is having atomic number 5, 1s2, 2s2, 2p1 is the electronic configuration. So if I take 2s2, 2p1, it is having 3 valence electrons. Ground state 2s2, 2p1. Excited state, 1 electron will jump to the next level. Okay. That is 2s1, 2p2. So this all 4 orbitals combining to form Sp3 hybrid orbitals. So we are in Sp3, we are having 3 unpaired electrons containing orbitals and 1 empty vacant orbital. So these 3 unpaired electrons of the orbitals Sp3 involves in bond formation with 3 hydrogens. So you can clearly observe. So another vacant orbital is with boron. So now these two borons are not having electrons to form a bond between these two borons. Okay, now we can say that diborane is having only 12 electrons here. Totally how many hydrogens? Bonds with 6 hydrogens. 6 hydrogens we are having 6 electrons, and each boron is having 3 electrons. Totally 12 electrons in the structure. So when compared to C2H6, it is electron deficient because it is having less than 2 electrons. So now this electron deficiency can be explained in the structure. So let us see the diborane structure now. Okay. So now we understood why the diborane is called as electron deficient molecule. So now let us see the structure in hybridization. So how the 12 electrons arranged in the structure. Okay. So according to electron diffraction studies proves that diborane has 2 coplanar BH2 groups and 2 remaining hydrogen atoms lies centrally above and below the plane. two coplanar BH2 groups. These two are planar BH2 groups. Okay, and two hydrogen atoms, remaining two hydrogen atoms lies above and below the plane. So this is the expected structure through electron diffraction studies. So now let us see the hybridization in order to understand the structure. Okay, so boron is having atomic number 5. So I am arranging the electrons in orbitals 1s2, 2s2, 2p1. So I am taking only valence electrons in the hybridization now. So in ground state we will have 2s to 2p1. Okay, in excited state one electron from 2s moves to the 2p. So 2s1, 2p2 now. So now these four orbitals s and p3p orbitals combines together to form 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. So this is sp3 hybridization. So now in these sp3 hybrid orbitals, 3 orbitals consists of one unpaired electron each and one is empty. Okay, out of this 4 sp3, 2 orbitals with unpaired electrons in the boron combines with 2 terminal hydrogens to form this terminal hydrogen bond. Okay, one boron which consists of two unpaired hybrid orbitals combining with 1s orbital of hydrogen to form 2 terminal hydrogen bonds. Okay, so one boron atom this side forms 2 terminal hydrogen bonds and another boron atom similarly forms 2 hydrogen terminal bonds. Okay, so now we are having one more orbital, sp3 hybrid orbitals, which consists of one unpaired electron and one more sp3 hybrid orbital which is not having electrons, which is completely vacant. Okay, so now this unpaired electron consists of sp3 hybridized orbital combining with 1s orbital of another hydrogen to form this bond. Okay, so now this hydrogen, 1s hydrogen, is combining with completely filled boron and vacant orbital of other boron to form banana bond or 3-centered 2-electron bond. That means this vacant orbital is from another boron and this orbital is orbital which consists of unpaired electrons. So this is called completely filled orbital because it is forming bond with this hydrogen and this this unpaired electron, both are forming bond. Then it is combining with vacant orbital. So we can say that completely filled orbital of boron is combining with vacant orbital of other boron to form a banana bond. This is 3-centered 2-electron bond. Why we call this a 3-centered 2-electron bond? Three atoms are involving, 2 borons and 1 hydrogen. 3-centered, but 2 electrons are involved in the bonding. 3-centered 2-electron bond. This is the shape of banana. So we can call this as a banana bond. So here also completely filled orbital of boron is combining with 1s orbital of hydrogen and vacant orbital of other boron atom to form a banana bond. Okay, so 2 banana bonds, 3-centered 2-electron bonds are observed in the diborane and 4 2-centered 2-electron bonds are observed. Those are no normal covalent bonds. 2-centered 2-electron bonds means 1 boron and 1 hydrogen. 2 centers, 2 electrons are involved. So 2-centered 2-electron bonds are 4. Those are nothing but 4 terminal hydrogens. Okay, and 3-centered 2-electron bonds are 2. 3-centered means here 2 boron atoms and 1 hydrogen atom. Here also 2 boron atoms and 1 hydrogen atom. So 3-centered 2-electron bonds are 2. Those are nothing but bridged hydrogens. Okay, these hydrogens are called bridged hydrogens. These hydrogens are called terminal hydrogens. So completely we are getting banana bonds. Okay, so here diborane is having sp3 hybridization and with 2 coplanar BH2 groups which are lying on same plane and but 2 hydrogens which lies above and below the plane. These 2 hydrogens are perpendicular to the other hydrogens. They are not on the same plane, but these 2 hydrogens are lying perpendicular to the other terminal hydrogens. Okay, so these are parallel hydrogens, these are perpendicular hydrogens. Okay, so this is about orbital diagram of the diborane. So you need to practice the diagrams and try to understand the concept by seeing the explanation. Okay, this is completely about the structure of diborane. Thank you so much for watching.